Well, I'm not really supposed to do this. I found something very, very cheap, and I just had to buy it. Normally these are really overpriced. This one was sold broken. It was in not working condition, parts only, no warranty, no returns, no accessories, no cables, no manual. Nothing was included. Incidentally, I got the original box. It looks like it's been through a war zone, but nothing else came with it. So what this is one of those portable power stations. I call them solar generators, only if they run continuously while under solar charge. A lot of these units, if you plug a solar panel in, the outputs will switch off, and that's just a power bank. And the retail on this is quite high. I got it for very little money. I could not resist it. It was so cheap. I don't know whether this will run or not. This is the condition I received it in. It's totally bricked. It doesn't do anything. None of the buttons work. And what you're seeing is exactly what I got in the mail. The specs are pretty impressive. 296 watt hours. I figured that by buying this unit, at the very least, I get a huge pile of 18650 batteries, and that'll more than cover what I paid for this. Anyway, I thought I would go ahead and take you through the process of what I normally do when I get a solar generator or a portable power station that does not work. I actually have over 40, almost 50 of these. Some were not working, and I worked on them, repaired them to varying degrees of success. In some cases, I was not successful. This is a unit I've never seen before. I've never had this particular one. So I'm going to see what I can do with it. One of the first things I would do when I get one of these devices in the mail that's not working is I'll shake it. And you don't really want to hear anything rattle in the case. On this one, there sounds like a wire or something, which is probably okay. Next, I would look at it to see if it's been dropped. And this unit is basically in mint condition. There's basically not a scratch on it. No significant scratch. Doesn't appear to be any dirt or debris or anything. In fact, it looks like it was never really used. Even the rubber feet on the bottom still have the protective covering applied, and that is barely disturbed. So I'm beginning to wonder if this was a return. Maybe it was DOA and it was just never really used. I don't really know. Also, I will usually use isopropyl alcohol and just sanitize it, because I don't know where it's been or what it's been through, and I'm going to be handling it and having it in my house. I don't really want to take any risks. And I use isopropyl alcohol for that usually. Next thing I would do, usually, I want to check the outputs and inputs. So I'll usually set a ohm meter on maybe 200 ohms. And actually I'll make it 2000. So the ohm meter is just going to measure resistance. And one of the first things I want to do is I want to see if any of the inputs and outputs on this thing are shorted. I guess I will try the DC outputs first. Those should not have any connectivity at all. And yeah, I'm not getting anything on there, which is correct. You shouldn't. Those should really be open circuit or very, very high impedance if there's nothing wrong. Nothing. I'm not going to bother with the USB. Next, I want to look at the inverter outputs, so the AC outputs. Now these often are shorted. It is common, but what I'm going to do is I'm going to measure across live and neutral. And normally this is not a problem. There's not going to be any voltage on here. It shouldn't be a problem. And try a higher setting. Not getting anything there. Okay, I don't think it was making contact. So very high impedance. Yeah, I did get a connection. And it's a very high impedance connection. Now this inverter, I don't know what kind it is. Some of them do have a connection between ground and live and neutral. I don't think that is common anymore. It's called a live neutral setup, I believe. So some of the cheaper inverters, I guess, would have power going from here to here and from here to here. I personally have not found an inverter like that yet, but I've heard they do exist. So I don't think this inverter output is shorted, at least on the output stage. I cannot test the input stage because that's inside the unit, and those also blow up. And I would consider those to be more vulnerable to blowing up than the output stage. But this is what I can check from the outside. And this is generally the process I go through. Next, I want to check the DC input, which is where the solar panel or AC adapter will be attached. Of course, for me, I would never want to attach an AC adapter. What's the point of that? I would want to attach a solar panel. Okay, I'm not getting anything there. Yeah, if I turn it up on a higher range, there's something there, but it's quite high impedance, so it's not a dead short. So Nothing appears to be shorted. Now for the next issue. This particular power unit has these famous triangular screws, which I think are quite aggravating. I think they're called safety screws. I'm not really sure what they're keeping us safe from, other than the ability to open things up and work on them that you own. But anyway, it has those types of screws. Now, of course, these types of screws, sometimes you can use a different type of screwdriver than what was intended. In this case, I'm using a minus screwdriver. There is a chance of it slipping and stripping out. But a while back, I had another solar generator that I opened, and I went ahead and I just bought triangular screwdrivers for it because it was so aggravating and so annoying to get inside the unit. I just went ahead and bought some. They weren't cheap, but this is the second time I'm going to be using them. I'm not sure which size it is. That's a little bit too loose. Try the next size up. That's still loose, but it fits a lot better. I don't know what size these are. I think they're measured in millimeters. This one is too big. I could use it, but it's too big. Anyway, I guess I'll try the next size down because it fits in better, I think. So I'm just going to start opening the unit up and take a look at it. There's 4 screws on each faceplate, but I think there's more screws on the side. So I have a feeling that this portable power station is just that. A lot of them are just glorified power banks. If you have a solar panel attached, the output's shut down. But I still intend to use this. If that's what it is, I'm still going to get a lot of use out of it. What I use them for, if I can repair them, is powering lights and charging my cameras. And very useful for that. And in this one, if I could possibly get it to work, at the price I paid for it, it will more than pay for itself many times over. If I can't get it to work, you know, I have at least the 18650s. That's better than nothing. It's certainly not a waste of money. And one of the screws is giving me trouble. I think we might have a missing screw here, so that could be an indication someone's been in this unit. It's very hard to see in there. I'll have to take a closer look. There does not appear to be a screw in there. I use a flashlight to eliminate the plastic. It's a really deep set screw. It's down in that hole. I don't think there's a screw in there, so either I took it out and I wasn't aware of it, or it's already been opened. So anyway, so now it should come apart. Yep, there's the back faceplate. Got a fan and a DC input. The plastic is actually this nice soft touch stuff. I guess it's overmolded, I'm not sure. It's got a kind of a rubber feel. There's the front. Now when opening one of these, you want to be really careful because there's probably high voltage in it, or there could be. If you don't know exactly what wires to touch and not to touch, I don't recommend opening one of these if it has an inverter in it. If it doesn't have an inverter, it's probably okay, but you should know what live and neutral is. You should know what a high voltage capacitor looks like. Otherwise, you're kind of risking yourself. You might get hurt. Now, one thing I do notice is there's a lot of sealant and goop and glue placed on the connections. Usually that's a sign that they care enough. They don't want the unit to fall apart. So that must be the USB power board. You can see all the electronics that drive it. USB, this has QC 3.0. I don't use that. I don't currently have a phone that uses it, but it's nice to have. Okay, let's see if I can get the... Hopefully I can get the whole thing open. Unless I missed a screw. And or there's screws underneath these feet here. It's very possible. Or the feet are just holding it together. Sometimes the feet, they're stuck on and they hold everything together. I hate messing them up. There's nothing I can do about that. If I want to open it, I have to peel the feet off. So I'm just going to take the rubber feet off. Hopefully I can get them to stick again if I use this unit or I'm able to repair it. I will hopefully be able to just stick those back on there. Maybe I'll put some extra glue or something, because I don't really want to give them up. And it does not feel like it wants to come apart. Oh yeah, it does. It was a little bit stuck. And this rubber thing on here, this handle, might be a problem. It looks like it's... yeah, I may have to pry this a little bit. Okay, it had some clips. And actually, this is the flashlight or lantern. So I should be able to just disconnect that so I can get this out of my way. Okay, there's the unit. Big gigantic battery pack. Hopefully the camera will focus. Okay, so the first thing I would look for when I open one of these, being careful not to touch anything. This is the inverter board. There's going to be some high voltage potentially, but I'm not touching any of that. First thing I would look for is I would look for pinched wires, because that is actually quite common. I don't see any pinched wires. I would also look for wires that have come loose. And I don't see any wires that have come loose, although you may find them later. And I would also look for signs of anything that got hot or burned. They even have safety screws inside, isn't that something? So I don't see anything that at first glance that looks like it got hot. I would also smell to see if I smell lithium. And if you smell lithium, it has a sweet chemical plastic smell. Probably means one or more of these cells is leaking, which would be a really bad thing. But I don't smell it. And I would look right here at the heatsink. If you look, it's kind of hard to see with this camera here. Move the light over this way. In there you can see some power transistors and diodes. I would look at those to see if they look like they've released any black smoke. It's not always going to be obvious if any of them burned, but I don't see anything here at all that indicates something burned or melted. Another thing you can look for is these capacitors. Are they bulged at the top? No, these aren't, but actually they look brand new. So you would just want to look at the capacitors and see if they've been venting their electrolyte, or maybe they're under distress or have gotten too hot. But I don't see anything like that. Everything in here looks brand new, perfect, shiny, like it came from the factory this way. So probably this would not be easy to repair. There's nothing obvious. The battery looks fine. I've moved the camera a little bit closer. It says it's a 300 watt board. That's what the circuit board says. So that's a 300 watt inverter. Who knows if it works. Next thing I'd like to do is, generally speaking, I want to look at the battery. Honestly, the battery is the most attractive thing in this whole unit. Everything else here is a bonus. This battery is what basically I'm hoping to salvage. I don't necessarily assume I'll be able to repair this unit or recover it. I don't really know. So I figure for the price I got into this, if I can get a nice fat battery out of it, that'll be more than worth it. It doesn't take a lot of effort or work. Now I'm looking on this battery pack for active electronics. I want to see if it has what's called a battery protection circuit. Wow, they didn't peel the 3M tape. I'm actually okay with that, because usually they're really hard to get out, and this battery just came right out. No effort required. So that's kind of interesting. Okay, so what I want to do now is measure the voltage of this battery and see if it's completely dead. My guess, it's totally dead. I'm going to try this as a camera angle. Seems to be a little bit better. So here's the main wires. You usually would look for the biggest wires. Here's some 12 gauge wires that are coming out. Looks like an XT60 connector. So these are the main battery pack wires, obviously. There appears to be two more wires. These are probably to provide the 12 volt DC output. And I need to see if this battery pack is protected. In other words, does it have a battery protection circuit in it? And or does it have active balancing or a battery management system? Anyway, let me go ahead and see if I can get a voltage on this battery. If it's flat dead, then I'm not sure there's going to be much hope to repair this unit. But I'm going to try to find a place where I can probe it. And here's a little connector on the side. Maybe I can get this off. Everything is glued together, so wow, it does not want to come apart. Okay, the glue is really tough on there. So here's a small connector coming off the left side of the battery pack right here. And I'm going to see if there's any voltage on it. 0.03 volts, so not looking good. So my guess here is this is a protected battery and it switched itself off. Okay, there's the XC60. Let's go ahead and power that on. Well, I'll connect the meter to it anyway. So I'm measuring the XC60 and I get the same result, about 0.03 volts. very possible that this battery has a protection circuit in it and it has shut itself off, and or it's very possible it's just flat dead, which is really bad. So I'm going to take the battery out. We're going to put that over on the side here. Now we have a board which potentially could function or it may not function. What I'd like to do is feed power into this board and see if I can get it to do anything. That would be one option. But before I do that, I want to go back to my ohm meter here. I'm going to switch it to 200 ohms, and I'm going to probe the DC input, that XC60 right there. Now we got to make sure we do positive and negative correctly, so I'm going to make sure and verify which is which. On the circuit board there's actually a positive and negative sign there, so when I hook the power up to this I got to make sure I don't hook it up backward. Okay, on the input I got nothing, so no short circuit appears to be on the input. I'm also going to probe this small power board which does the USB and all of that, see if there's a short on that. And there's not. On the right hand side I have my bench power supply, and I've got a bunch of wires hooked up to it. I've got a split on each side coming off the positive and negative because I need to be able to feed power into this board. I also need to be able to feed power into this small connector in the lower left hand corner of the screen. And that is because this left hand side board here, you can barely see it. It's right here on this side, right here. And there's a small plug that goes to the battery. More than likely this is the board which handles charging and also has some brains on it. So it probably has some voltage regulation, who knows, but it's got to be connected to the battery. It's got to have power fed into it also. So I'm referring to this small connector here. Actually, this setup is quite common in solar generators and portable power systems. There'll often be a pair of very large wires coming off feeding power into the main board here, and then there'll be a smaller set of wires going to a different area, and those handle usually charging and low power requirements. And sometimes there'll be even more wires. In this case it's quite simple. There's only two sets of wires going to the battery pack, and there's nothing else. After checking the polarity, I fed the 12.73 volts as you can see on my power supply, and that's set to about an amp or less of current. It's a current limited power supply, and I fed that power into the main power board here, which has got the inverter on it. I also fed these two alligator clips. You can't really see them because there's limited room in the camera field here. I've also got a set of alligator clips here that are piggybacking on the power supply's positive and negative output, and those are feeding power over to this small plug here you can see in the lower left hand corner of the screen. And that is the front panel of the unit that has a circuit board. Most likely this is where some of the intelligence is, so you have to power both boards. If you power only one, it's probably not going to work. So the first thing I'm going to do is I'm going to do something really simple. I'm going to attach the lantern or flashlight cable, which is this ribbon cable right here. I'm going to plug that back in, and I'm going to press the button on and see if I can get the light to come on. I'm guessing the camera's not picking up all the action here, but I'm using what I have. The footage is a little bit dark, and sometimes it's washed out and it's hard to see things. Anyhow, I've got the flashlight hooked up. This is the outside portion of the unit with the flashlight on it. What I'm going to do is I'm going to push the button on this flashlight or lantern portion of the unit and check the power supply display on the right hand side. And let's see, it's set at 12.7 volts, which is actually a bit on the high side. I might lower that. Let's just lower that down to, I think 12.4 volts is more reasonable. I had it a bit too high. Let's go ahead and turn on the light and see if it'll do anything. Boy, that's bright. So it did come on, and you can see it's drawing, if the camera will focus on it, 12.42 volts, 0.758 amps. So, you know, it's drawing about 9 watts. So obviously the unit is alive. It just wasn't getting power. And now that I fed it power from a power supply, it's come alive. Now the question is, does that also apply to the unit's front panel? Because the flashlight turning on is not necessarily good enough. So what I'm going to do is I'm going to turn on the front part of the panel, which is got the display and everything else on it. Now in order to show that on camera, I'm going to have to move things around here, so I'll be right back. Okay, I've managed to get the unit turned around in the camera frame. Hopefully my alligator clips didn't come off. Looks like they're still on there. So now I'm just going to try pressing the power button, not the AC button, but just the power button, and see if I get any action. Came right on. It currently says the battery's empty. USB 5 volts, quick charge I guess is what that one means. I don't know what that means. That must mean the DC outputs are on. Actually, let's go ahead and test these outputs and see if they're doing anything. Well, I'm having trouble getting everything in the camera frame because I want to be close up to it, but I also want to be far enough away to see everything, and it looks like there's a balance to strike. But anyway, you can see the front panel of the unit is here, and you've got your USB, your QC 3.0, USB 1, USB 2, 12 volt, Type-C. We're going to plug something in that's USB. This is just a light, and I'm going to turn the unit on. It looks like it powers itself off if you don't put a load on it. And I'm just going to see if these USB ports are putting out 5 volts, because if they are, that's a good sign. Yeah. That one's working. That's also working. And so is the third one. All 3 USB ports are putting out power. Now I want to check the 12 volt output. To test the 12 volt output, I'm going to plug in this 2.1 millimeter barrel adapter. And let's see if we're getting any power out of there. Put my meter on 20 volts. Oops, it turned off. Turn it back on. I'm getting 12.58 volts. Actually, I'm getting what appears to be battery voltage. So all of the outputs appear to be working. Now, the next question is the inverter. Does the inverter work? So I'm going to test the inverter. I got to be a little bit careful because I don't want to electrocute myself. Now I'm going to test the inverter. Before I do that, though, there's something I need to check on the circuit board. I had some interruptions, but I'm back at it. I managed to take the inverter board out, and I did some probing. And indeed, the inverter board is not running. It is powered on. It is trying to work. And so it looks like this inverter is not producing high voltage DC as it's supposed to. And that is referring to the boost stage on the inverter. So an inverter like this uses low voltage DC. That's what you put in here. This would be the battery. But that isn't high enough to make AC, which is around 110 volts. Incidentally, this transformer here says 110 volts on the top. The problem is that when I power this inverter on, I made the comment that it must be very efficient because it wasn't using much power. Well, that's because it isn't doing anything. The inverter does power on, and I suspect that these transistors, which are here, you can see them right there, there's 4 of them all in a row, I suspect they are being modulated because they all have battery voltage on them. I do not have an oscilloscope, so I can't see whether there's a waveform on here, or a square wave. I can't look at the signaling on the base of the transistors, so I can't see if there's any activity there really. What I can do with what I have is I can measure the transformer taps, and I can measure the inputs of the transformers. And I'm getting low voltage there, but I never once saw high voltage DC. So I suspect that this transformer here is burned, or shorted, or has failed in some way. Now I don't have one of these, and I'm not going to rob a working inverter to get one. It does have a number on top, but certainly with this number there's a chance I could maybe find it. I probably won't repair it right now. That would really be a long video. And I'm not 100% that this transformer is at fault. And again, I don't have any way of measuring the waveforms to see what these transistors are doing. They could just be sitting there doing nothing for all I know. It looks like they are switching. Over here you have a bridge rectifier. It's these 4 components here. They're a little bit hard to see because they're stacked up, but there's 4 of them, and they're all the same from what I can tell. And then you have this big capacitor here. This is supposed to hold your 200 volts or whatever it is DC. And again, I couldn't find any evidence of high voltage here. I have not tested these diodes, and actually that would be a good thing to do. But I don't think there's anything coming in here. I don't think it's the diode's fault. But yes, actually measuring these diodes and checking them to see if they function is a smart idea. Further complicating my attempts to repair, this inverter has a coating applied all over the bottom of the circuit board. With these probes I have, it's really hard to get a connection to measure anything. So what I've been doing is taking the meter probe and scratching away. And I think I got these 4 points here pretty well scraped. And that allows me to take a measurement of the diode to see if it's working. And indeed they appear to be working. So I don't think it's a diode problem. Those diodes look really nice and clean, and they're not cracked or burnt or anything. I don't see how they could be faulty. And it looks like that is a diode, the way a diode should respond. I don't know how accurate my meter is. It should not conduct one way because it's a diode. Yeah. So this coating is just slathered all over the board. And sometimes you'll think something is not conducting when it actually would. This is the 4th or 3rd diode that I've checked. Yeah, It's as expected. All 4 diodes check out. It would only take one failing to ruin it, but no, the diodes are all good, so I had to do my due diligence. So it's not the diodes, and I don't have any easy way of checking the capacitance of these capacitors, but they look really good, so I think they're fine. Now the taps of the transformers, if I were to take this transformer out, and these are the pins to go to the transformer, I could measure the taps on the transformer and try to figure out if any of the coils or windings are burned. I don't want this video to be too disappointing. I don't think there's going to be an inverter repair in it. I'm fairly certain I have diagnosed the fault here, and it's this transformer. It would be nice if the failure was obvious, but it just isn't. Electronics a lot of times are very ambiguous. They really don't necessarily show you anything. And I'm always looking for a burn spot or something easy, but that's easy. It's really hard when the circuit fails and there's nothing physically obvious that tells you that it's failed. I know the diodes are good. I know we're getting battery voltage here. I know these fuses aren't blown. And I know these transistors are getting battery voltage as well. But I cannot find any functionality beyond that point. Once I get to this transformer, that's where everything stops. It's logical to reason that either these transistors are not switching properly, and I have no oscilloscope to confirm that, or this transformer here has been burned out. Maybe if I do get to repairing this board, I will pull this transformer completely out and maybe try to find a replacement for it. It's probably not very expensive if I could find this exact same transformer. I'm not willing to bodge and put some strange transformer that doesn't belong in here. I want the exact same thing. Otherwise, what's the point of repairing it? These components here, it's actually quite simple. And where it gets complicated is, this is the logic, this is the computer board that controls the pure sine inverter. Pretty sure it's a pure sine inverter. I haven't looked at the specs, but if you look on this board here, you can see there's what appears to be probably a microcontroller. There's quite a lot of stuff on here, way too much circuitry to just be a simple inverter. A square wave or a modified square wave inverter probably would not have quite this much intelligence in it. However, the components in that inverter would be very, very similar to what you see here. And the reason I don't look at the specs of this unit is I'm challenging myself to figure it out by just looking at the board. And I hope that by doing that over a period of time, I'll gain more and more knowledge and experience. And later on, I can always look at this unit and see what the specs are and see, was it indeed a pure sine wave inverter? And also, maybe I made a mistake in identifying certain components, and I'll learn about those as well. I'm still pretty slow on identifying common mode chokes, filters, things like that. These are things that you pick up over time. And my dad was a self-trained electronics engineer. He never set foot in college. I know if he taught himself, I can teach myself too. And by the way, this has a nice little fan here, which incidentally would fit my MPT7210A charge controller. This is a 40mm brushless DC fan. It's glued on though. All is not lost. If I decide to just remove this board or just not repair it, there's some good stuff on here, and I could actually use this to repair other inverters. Now, I did not overlook that there are 2 temperature probes here. I'm actually kind of scratching my head. Looks like a temperature probe here, but there's also one right here, and I do not know why they have 2. Now, what I will tell you is these go bad all the time. It's quite possible that this inverter thinks it's overheating because these temperature probes here are not giving the correct reading. And I can't be bothered right now to unglue and unscrew these and tear them out of the board and measure their resistance, look up the part numbers and see what the resistance should be, because my guess is they're probably working just fine, just like the diodes, and it really is just a problem with this transformer. So maybe later I'll look for a new one, see if I can find it. On the back of the inverter, I wanted to point out that this is the high voltage cap, and I suspect that this resistor has been placed there for safety. So I think this is probably to bleed down this high voltage capacitor as soon as the unit is powered off. This resistor, which is shorting out this capacitor, would eventually drain this capacitor of its high voltage charge. But be careful, because many inverters do not have anything like that. Many circuits do not have anything like that. And so if you were to just take your finger and place it right there, you would get an unbelievable whack. You would really wake up. Whatever you were doing, you would stop it. You would notice. So I just wanted to point that out. It's really interesting how they were thoughtful enough to put that resistor there. They didn't have to do that. So if indeed that's a bleed resistor for the capacitor, I'm very impressed that the engineers were so thoughtful to put that in here. Another area that I investigated is this red wire. If you look here, there's a red wire going into a plug, and there's no black wire. It's just a single red wire. You can see the hole on the right side of the red wire where the black wire would go. And what this is to power the inverter on. And the reason why there's only one wire is this wire here is in reference to ground. And what it does, it feeds, I think 3.3 volts up into this inverter board and tells it to power on. Or rather, it probably tells this board here to power the inverter on. So that's not a problem. That looks like a missing wire there, but it's not. It's just a power switch. Incidentally, if you took this inverter board out of the unit and repaired it, you could use it on its own. If you were able to use this connector here to turn it on and off, you would have yourself a little 300 watt inverter board. You would not need to leave it inside this unit. That's why I would never throw this away, even if I don't repair it. I might use it later, and this could be very useful. That having been said, I think I'm going to skip the inverter part now and go straight to the battery pack. The battery pack is the main draw of the unit. I hope it's good. I don't know if it is. I don't have a good feeling about it. I did see this unit power on. I saw the display come on, the USB ports work, the DC outputs work. I believe it's a regulated DC output on this unit, which is not exciting because I'd rather have full battery voltage present at the terminals. But you'll see why they did that in just a minute. If you're going to buy it for scrap price, you would want to know what the status of this is. And I felt I might have been wrong about the voltage. Indeed, it's a 14.8 volt or 4-cell system. I had a suspicion that I was feeding only 12.6 volts into the inverter. I thought 12.8 volts would be too high. Actually, it was kind of low. I did try putting a higher voltage into the inverter. Same result, didn't change anything. Still acts the same. This is a relatively new battery pack, April of 2021. It's quite heavy. As I showed earlier in the video, it is not putting out any voltage. But let's go ahead and verify that one more time. Let's see if it's still doing nothing. So this is the main output. Yeah, basically has nothing on it. This is probably to charge the pack. My suspicion is you charge through this. Yeah, same result. So I'm going to try to wake this battery up, but I really want to know if it has an active protection circuit in it. And I've been feeling all over this battery pack, and I can't find a circuit board. All I can feel is the cells. And I really do not want to cut into the heat shrink wrap on this thing. There could be a circuit board under here, and I just can't feel it. Maybe I can get some of this tape off without doing too much harm. I can feel the battery cells there, so I don't think that's a circuit board. Very strange. Could it be that this is a... It can't be a pack with no battery protection circuit. I just can't believe they would stick that in a portable power unit and sell it to people. So I might just have to tear open the heat shrink. I hate doing that. Before I do that, I'm going to try charging the battery a little bit through this connector here. I suspect this is for charging it. The reason why I suspect that, and this is the front faceplate of the unit, and right here you can see I tore off the plug, and that says in positive and in negative. And that was where the DC input was attached for the solar panel or AC adapter. Incidentally, this little plug here comes off the same circuit board. My suspicion is there's a charging circuit on here. Probably even, it might even be this chip right here. Anyway, the point is this circuit board obviously has something to do with the charging because the charge current is passed into it, and the battery's smaller cable is also on the same circuit board. So there's probably some kind of intelligence on this board that tells the charger to turn off. That is my suspicion anyhow. I'm now going to attempt to charge the battery. I hope it does something. I'm using my little bench power supply here to do that. It's connected to a couple of 100 watt solar panels, and I use this little power supply for all sorts of reasons. And it's really handy just to, if you want to put a little bit of power into a battery and trickle charge it. A little power supply like this isn't going to handle a lot of current, but it's better than nothing. And I'm going to set the current to something really reasonable because I'm not really sure what the condition of this battery is. So let's turn it on. Actually 100 milliamps seems fine to me. I'm just going to use 100 milliamps. That is actually a little bit high. If this battery was down to 0 volts, I wouldn't put 100 milliamps into it. I suspect that it isn't, and I'm just going to risk it. Let's put the voltage up to something high. It needs to be... I don't know what the voltage of this battery is in its current state. My guess is it probably isn't 15 volts or 14 volts. So now I'm going to try to charge this battery pack. I'm going to try to back probe this connector like this. It's a bit tricky. You don't want to short it out. And see if I can get any charge into this battery. Got to be careful not to short this out. Nine volts. Let me turn that current down because if this battery's that dead, it needs to be less than 100 milliamps. So I put it down to 30. 9.3 volts, 9.29 volts. It's hard to tell if it's actually charging. Okay, let's see if this voltage creeps up. 30 milliamps is not very much. And just to be clear, if you have batteries, lithium-ion cells that are down to 0 volts, and I have no way of knowing what the real voltage of this pack is, you do not want to dump current into them because you'll destroy them. It's better to put a tiny trickle charge into them, even 1 or 2 milliamps, and just leave it overnight, or just for several hours, and hope that the voltage will slowly creep up. One of the reasons is that sometimes the cells could be near reversal. That means their polarity might swap, and you don't want to dump a bunch of current in. And when the cell is discharged, it's very weak. It's in a vulnerable state, and dumping current into it will just magnify the damage. So if you're trying to recover a lithium-ion cell, the last thing you do is dump current into it. You put a teeny tiny trickle charge, and you just be patient and see what happens. In this case, I suspect this battery pack was probably, what would 9 volts be divided by 4? It's really around 2-something volts, so hopefully this battery pack has a circuit board inside which protects it. That's why I woke up to 9 volts or 8 volts, because it was in a deep sleep state. But again, I'm just speculating because I don't want to tear this battery pack open. You know, I'll probably end up doing that anyway. Right here you can see the wires go in. If there was a protection circuit, it would be connected to this pack output and this charge input for sure. That means the battery pack must have a circuit board, if it exists, somewhere right around here. Maybe I can just cut some of this off here. It's not going to look nice. We're up to 9.5 volts. You can see my power supply is reading 9.6. Who knows how accurate that is. These alligator clip wires are incredibly skinny, so there's going to be some voltage drop. 9.52 volts. It looks like this battery pack was totally discharged and switched itself off. Now, sometimes you can recover them by simply charging them. Other times you can't. Well, this battery pack appears to be functional, at least at first glance. It's now up to 11.3 volts, and I'm now going to probe the output, and the output has been turned on. So what you have here is, this is a battery protection circuit. What I'd like to know is it a battery management system? In other words, does it do active balancing, or I should say shunt or resistor-based balancing? Because this battery was run all the way down, and I have no way of knowing what the individual cells are at. I think what I will do is put a small charge in this battery and reassemble the portable power system and give it a test. Now I suspect that this unit, if I had just plugged a charger into it when I first got it, it might have recovered from its brick state. And some of them will, some of them won't. The reason why I didn't do that is really standard procedure. When I get a unit in the mail that is sold for scrap price and it's not functioning, I always disassemble it and check the inside in its current state. I don't want to modify its current state, which is a failed state. And I want to check everything, check all the voltages, the fuses, and everything inside in its actual state before I try charging or plugging anything into it. So that's just a standard procedure whenever I get one of these generators. I have many of them now. Some of them I've worked on, some I bought brand new, and anytime I get something that's in the mail that's unknown status, I usually am very cautious. I don't want to just plug it in and leave it there. Usually I try to learn something, look at everything, look at all the evidence first before changing anything. And that's just the general rule of thumb that I follow in most cases. Now that the battery pack is around 12 volts, I hope that means for a 4-cell system you've got about 3 volts in each cell. Again, I have no way of knowing because this has a smart system inside the battery that keeps me from looking at the true state of the battery. Hopefully the cells are somewhat in balance. What I'm going to do now is I'm going to attach this battery pack to the unit itself, and I'm going to try to charge it as it was intended to be charged, all put together. And I got to be real careful with this one. I need to reconnect the charge port, and I pulled the whole plug off the board, so I got to make sure and get the polarity correct. It says positive is on that side, negative is on that side. I can't mess this one up. Okay, I think I got that on there. Now I'm going to see if I can get a charge to go in. Now what I did not show, I probably should have shown this, is that as soon as I unhooked the charger from this battery pack, it went back to 0 volts. So it's very possible the battery is also bricked. I don't know that for sure, but I'm going to give this a try. I did give it a jump start. Alright, let's see if I can get some electricity going into this thing. I'm going to use my current limited supply to do the charging, if it'll even accept a charge. Let's go ahead and plug it in. Yeah, it's not good. It says it's, yeah. Hard to say. It's acting like it can't make up its mind. Yeah, what it's doing here is not normal. I don't think this is normal behavior. It's acting like it can't charge. Now, that in and of itself is not the end of the world, because I could actually attach my own charging circuit to the battery. The question is, can the battery take a full charge? If this charging circuit is malfunctioning, I can still use this unit by putting my own charge circuit in it. But right now I want to run a real quick diagnostic test to see how useful is this unit really, and I'm going to try to turn on the inverter. Okay, so what you have here basically is not a solar generator. So what this really is a USB power bank with DC outputs, and happens to have an inverter. After seeing the results of the test where it's under charge and I attempt to turn on the inverter and it doesn't work, repairing the inverter on this unit is no longer interesting, because this unit would be useless as a solar generator. It's not a solar generator, it's just a USB power bank with a inverter on it. And right now it's under doubt that it can even charge. It appears to me that the power is cycling on and off, the battery's cutting itself on and off. And so what that means is there's probably something wrong with the battery pack, and or the charging circuit, possibly. Let's see if any USB power is coming out. It's probably going to be turning on and off, that's my guess. There's the USB light. Yeah, it's turning on and off. So not normal behavior. So this unit is in a failed state, or the battery's in a failed state. What I will need to do is look at the battery pack a bit more closely. Well, it's like everything else. I'm going to force myself to cut into this battery pack. I don't want to do it, but it's scrap, and it was sold at scrap price, scrap value, and I don't have a choice. I could just charge it, but that will always leave me in doubt. What is the state of the actual battery pack itself? Now, this battery pack did accept a charge. That is a fact, and it was charging up to a decent voltage, although still discharged, mostly discharged. So I have a choice of just going ahead and charging the battery overnight or for several hours, and then seeing if this output here will stay on. See, what's happening is the battery's switching this off, and that makes the battery pack useless if it does switch off and stay off, but you can't use the battery. This is the main connection for discharge, this is the main connection for charging. So I have a choice here. I can go ahead and cut it open, take a look at the cells to see how they're balanced, or I could just leave this on trickle charge for a while and see if this output here will stay on. If it does, then this battery probably can be saved. Back on charge for the moment while I decide what I want to do. And it's taking a charge now. It's 800 milliamps. So it's taking about 9 to 10 watts of power input, and it is not terminating the charge. Normally a battery protection circuit, if anything goes wrong, it will terminate the charge right here and will not let you charge the pack anymore. Some of these have a board in it that actually has to talk to the microcontroller on inside the system, and it will not let you charge or do anything at all until it talks to that microcontroller, unless you bypass it. This one is a more traditional system. It just has a charge and discharge lead, and if you start charging, it accepts a charge if it's able to. The problem is, as soon as I take the charge off, this is disabled. But that could be because this battery was deep discharged, and it's decided that the voltage is just too low to allow the pack to function. Well, as you might have guessed, I'm going for the charge technique. I'm not going to cut the battery pack open just yet. First, I'm going to see if I can get it to behave normally and recover it, since it has been deep discharged. Nothing is getting hot, and so I'm going to give it a chance. To cool my power supply, I just put a little USB blower on here, because they do get warm. And all this is running off of solar. All the lights, the camera, everything. This bench power supply can also read in watts. Although it's not perfectly accurate, it's putting about 9 watts in. This is a fairly large battery pack. It's almost 300 watt hours. Normally, if the battery pack was not able to charge, you wouldn't see any current flowing here. No current would flow, or very little, and the voltage would skyrocket to whatever you set your power supply to. This battery is not acting that way. If you look here, my voltage is about 15 volts. That's what I have this power supply set to. As you can see, it's pulled it down to 12.8, although that's not actually what the battery's at because there's very thin wires connecting it. And we're getting about 10 watts into the battery, so it's actually taking a charge. That power is not just going into thin air, it's going into this battery. So I'm going to give this battery a chance, give it a recovery charge. Obviously, the portable power system is incapable of properly charging it. It's incapable of recovering from the state in which it was found, and that's probably why it ended up on the scrap heap for sale at such a cheap price, because the person who had it could not figure out how to get it to charge, and so it's basically just a paperweight. About a year ago, I did a video. This is one of my first YouTube videos, and I entitled it, "What is a solar generator?" And so I'm really duplicating a lot of effort here, but I just wanted to go over really quickly what makes a solar generator actually a solar generator. Well, to me, it should be able to handle a solar panel connected to it, and all the AC, DC, and USB outputs should continue functioning without any interruption. A device that shuts off the outputs when it's charged is nothing more than a power bank. That's all it is. That's all it'll ever be, unless you modify it. A solar generator is a portable off-grid system, meaning that you can continuously use power from it in any form, whether it's under charge from the sun or not. Now, the engineers who design these devices have a bit of a problem. They have their work cut out. You have the bean counters, which don't want to spend a lot of money, and they want to cut every corner they can. You have the attorneys and the legal department that doesn't want to be blamed for, the USB port melted and fell off and melted my carpet, and therefore they get sued. Then you have the true electronics engineers who want to design something that works really good. And so those folks know that if they design a unit that can be powered continuously and have an AC output, somebody's probably going to plug their computer into it and use it as an online UPS, for which purpose it was never intended. In addition to that, when you have electronics operating inside a small portable case, heat will slowly build up. This is a problem, and thermal management is a big deal. Sometimes they just stick a cheap brushless fan in there and call it a day. One of the designers or engineers' fears is probably that as the inverter is running and the DC outputs are running and the USB outputs are on and the charging circuit is in operation, all that heat is going to build up and eventually burn the unit out. They cannot stop a user or customer from plugging a computer or something into it and then plugging it into the wall and calling it a day. They absolutely can't stop anybody from doing that. So this is probably why a lot of these cheaper units, even the more expensive ones actually, will not function on the outputs when you plug in the power. But solar people, solar enthusiasts, people like me, all we care about is can we continuously charge off a solar panel. I don't care about AC adapters. I'm not going to plug it into the grid. All I care about is can I use it as a portable off-grid system. Think about people who are campers, RV people, people who like yachts and boats, people who like camping and traveling. They too would like to be mobile in the field, charge their unit off of a solar panel, and meanwhile continue to use all of its outputs to their fullest extent as they need, whatever the situation calls for. To me, that is a solar generator, and unfortunately many of the units on the market even call themselves a solar generator, but they are not. Another term I've heard is pass-through charging. Some of these units will be listed with so-called pass-through charging, but that still doesn't answer the question. Does the AC inverter continue working? Do any of the outputs shut off when the solar panel is connected and the charging begins? They don't always answer that question or make it clear. As a rule of thumb, I never buy these units unless they can absolutely support full off-grid operation continuously 24 hours around the clock. However, I have several of these units that function as a portable power bank, and I got them for very little money or at a cheap price, less than retail, and I used them to spend time repairing or learning electronics, and so that was their purpose. So this type of unit I would use for running lights and charging my camera, and that's about it. I'm not going to try to fix the inverter. It's not interesting. It would just turn off as soon as I plug the solar panel in, so that's pretty boring. However, this could be very useful for working in my shop and running all sorts of electronics, and that's what I use them for. If you're interested in seeing what a solar generator can actually do, check out some of my uploads. I have one video where I cooked some meat and vegetables in a crock pot using a solar generator that was being charged continuously with a small set of solar panels, and although the unit ran quite hot, it managed to get through the tests, and actually the battery did not completely discharge. Why is it so important to be able to plug in a solar panel and continue using the outputs? Simple, because it treats the solar panel or the sun as an addition to your battery. Your battery might have been able to go 1 hour, But if you plug in the solar panel, it can go 2 hours or 3 hours or indefinitely. It might even charge the battery slowly while you're running your camera or your lights or your laptop or whatever else you want to plug in. To me, that's the beauty of a true solar generator. It gives you extreme flexibility and it has a lot of different use cases. So my plan is to try to salvage this unit as a portable power bank with USB and DC outputs. Ignore the inverter, it's not worth my time. And try to recover this battery because it's pretty big and I hope the capacity is not ruined. And if I can do that, if I can get this unit at least working on the USB and DC outputs and the battery reliably charging, then I have myself a pretty nice machine. Otherwise, probably we'll just scrap it, take the parts out and use it for parts. I'm going to put a pretty decent charge into this battery. I'm going to try to hit 14 volts or something like that. Then I'm going to try again to see if it will charge in the portable power system by itself. If the battery cells are good and the battery protection circuit is at fault, which is possible, all I would have to do is tear open the battery pack, remove the battery protection circuit, attach my own active balancer, and probably then it will charge just fine. I seriously doubt the power system's electronics board has any clue what's going on with the battery. It isn't going to know that I disabled the protection circuit, and I could also insert my own charging circuit into this unit if I had to. I've done that before and it works pretty good. Anyhow, I'm going to cut out here and cut back in when this battery has a half decent charge in it, probably 14 volts, and then we'll continue on from there. It's the next day and I've been charging this battery a couple hours, 2 or 3 hours at least, and it still shuts off the outputs. So I'm not really convinced that the battery protection circuit on this thing is working as it's supposed to. I've lost patience with it. I'm just going to go ahead and cut it open and access the battery directly. I'm pretty sure there's a circuit board right at this end here, and I just need to remove this covering here. It's not too bad, and the circuit board should be right here, I'm pretty sure. I have to be a little bit careful because this is a live battery and I don't want to cause further damage. I saw the USB ports and DC output ports on this portable power system function, so I know those are good. So if I can just get the battery to behave, I would at least have a very large USB power bank. And that, for me, would be attractive enough to make a little more effort and try to salvage this. So that is what I'm going to try to do. You can see the wires go down inside. Yeah, it looks like there would be a circuit board right here. Hopefully I can get to that. Looks like they've got it double heat shrinked, which is good. Now I got to be really careful because I'm going to cut into the heat shrink. And I don't want to short this out. This stuff is really tough. Yeah, there's some cardboard. Alright, the cardboard is going to help me. So yeah, this is why I don't like tearing up the battery packs, because it's kind of ruins the appearance, but it isn't really how it looks, it's how it works, and right now it isn't working, so if you want it to work, you have to tear it up. I will trim off all of this excess later. Right now I just want to see if I can get to the battery and measure the individual cells. I have a suspicion that possibly one of the cells is not balancing, or is not balanced, and this circuit is not capable of balancing it. Well, that's interesting. This is actually a fairly heavy-duty BMS here. This looks like an actual BMS. It's not one of the little cheap ones. So you can see the heavy wires coming in. This is your charge. And I'm guessing there's a balancing circuit underneath here, so I'm kind of sad that this isn't working, because this is not a cheap circuit like you normally find in these packs. You normally don't find anything like this. This is a really, really nice battery pack, and I will probably use it inside the unit itself, but if you go around looking to price something like this, they aren't cheap. So yeah, really scored if I can get this to work. Wow. Okay, there's your main inputs. So what I'm going to do now is measure the actual voltage of the battery, which I have never been able to do because this thing is sitting in between. This whole circuit isolates the battery from the user, so you can't actually access the battery directly. I've never once been able to really see what the true voltage of this battery is. 13.7 volts. Yeah, this battery is pretty deeply discharged, 13.7 volts. Let's see how many volts that is per cell exactly. So at rest, not undercharged, and divided by 4, 3.425. So that's Pretty well discharged. I don't understand why this battery is not producing a current on the output. It should be. Yeah, it's turned off. So the battery is not putting out current. Yeah, it's not doing that. That's pretty annoying. So I wonder if what it needs is more charge. I guess that's possible. I'd like to see where to access the individual cells. Actually, that may be what that is. Let me see if there's a current on there. Let's see, battery positive. That's your negative. Let's see if there's anything on here. No. That's the, those look like balancing resistors there. Just speculating. I'm really afraid to stick my cutters in here anywhere because I don't want to cause a short. And there's always a chance. If you start poking around in something like this with metal tools, there's always a chance you can short something and then it's even worse. So I don't want to do that. I cannot see the management connections for the individual cells. They're probably hidden under here somewhere. And I would have to tear off some more of this heat shrink. But this big piece of metal here tells me there's a heat sink and there's a balancing circuit underneath that would get hot. This was getting a little hot while I was charging the pack. Also, it looks like they removed the label here. So there was a label here to tell me what type of BMS this is. But they've removed that, unless it's stuck underneath here. No, it looks like it was removed. Best I can tell, the label's been removed, so there's no hope of me finding, just by looking at it, which BMS it is. Well, cutting open the battery was a smart move. This is not the first time I've seen this happen. So what's happened here is one of the cells in this battery pack is nearly full. One of them is mostly discharged, and another one is basically flat dead. And I have seen this happen. This is not new. But I'm going to go ahead and measure the cells. I was able to uncover the connections for the cells. There's a temperature sensor right there. And you can see right there is B2. That's battery junction 2, battery junction 3, and somewhere on here is battery junction 1. It's hidden underneath the cardboard in the lower left-hand corner. So I'm going to go ahead and measure each of the cells individually, starting with ground. We'll see what the individual voltage is for each cell group. There are 4 cell groups in this pack because it's a 4S system. First we have ground, which is going to be negative, but I'm going to take that from the actual negative of the pack, not the BMS. So right here. And B1 is hidden right over here. And you get 2.1 volts. So 2.1 volts, that is over discharged. So there's battery 1 with reference to ground, which is right here. That's the true battery pack negative, not the BMS negative. Now I need to find 2, and 2 is actually right over here. It's kind of strange. Between B1 and B2 I get 4.1 volts. I hope that's focusing enough there. So that's basically full. Now between B2 and B3, 3.3 volts. Not discharged, but nearly so. Now between B3 and positive, let's measure that cell. That would be your 4th cell. 4 volts. Actually, I've got the meter backwards. 4 volts. It's out of whack. What I'll have to do is solder some wires onto these connections here, directly onto the battery, bypassing the BMS. I don't have a choice, I have to do that. And try to get this battery balance charged to see if it will work again. It's very possible that the whole reason this battery pack failed is simply this thing right here. Okay, so I'm going to do some emergency modifications to this BMS here. This really doesn't work for me. Most likely the BMS has failed in some way. I'm not really sure. My guess is it probably has. It certainly failed to do its job, which is to protect this battery and keep it in balance. It absolutely failed to do that. So what I'm going to do is I'm going to attempt to solder wires onto these access points here. And this will allow me to attach balance headers. I do not have any 4-cell balance headers in stock. I ordered some. What I do have is I have an active balancer and I have an active balancing cable. which I can plug in temporarily to try to get this pack balanced. Now I have this heavy-duty thick cable, which is a cable that was included with a active balancer, flying capacitor's active balancer, and I can use that to balance the pack for me without much effort, other than attaching these wires temporarily. The reason I'm attaching them temporarily is I don't have the proper cable and I don't have the right equipment or setup here. This is just temporary to see if I can get this battery working, and also to prove whether this BMS here has failed to do its job. Could be it just went so far out of balance it's unable to recover. Maybe the battery was abused. I don't know. I have no way of knowing that. So I'm going to give it a try, and I'm going to manually balance the pack using my active balancer. Then I'm going to just see if the BMS is able to keep the pack in balance. Really, the best thing I could do is just take this off. These really just get in the way. And I don't mind a battery protection circuit that shuts off when the voltage is too low or too high. In order to set this up, I need to connect the negative side, which is going to be quite difficult because it's a very large connection. I need to connect the negative side of the battery pack, which is right here, to the black cable here, which is temporary. So I've heated my soldering iron up and I'm going to give it a try. And I'm just looking to melt the solder enough to hold it on there. It's not the best connection, but really I just need a temporary hookup. Next is a green wire, which is going to go to, I think that's B1. And B1 is hidden over here. So, and there's a temperature sensor there. I don't want to hurt that thing. So I got to be careful not to melt that or hurt that in any way, because then the BMS will probably stop working altogether. So this is a bit tricky, especially with a camera. Let me just see if I can just bodge this on here real quick without shorting anything out. And it looks like it took enough to pass some current. Next we have a yellow wire. This goes to battery junction 2. And it looks like that little white wire there is barely hanging on. But let's see if I can do this. It's pretty tight here, this connection. Okay, there's B2. Make sure it doesn't short. And then I have a white wire which goes to B3. And that's right over here. Let's see if I can heat that up enough. Oops, gotta be careful. And it's not the beautiful solder joint I was looking for, but it'll have to do. Next I have a blue wire, and that's going to go to the pack positive, so I have a total of 5 wires. So here's the blue wire, and I got to get this on the positive side. So let me see if I can get it right there. Yeah, this is going to take heat. Actually, it flowed in the middle there, so these are big connections, but this soldering iron, I'm using my Ryobi soldering iron. It seems to be pretty powerful. So this is my blue wire. See if we can go ahead and pop that on there. Yeah, not a very good connection. Okay, that one there is a little bit harder, so I'm going to have to get that hot. Okay. All I'm doing here is making a temporary connection to the battery with my heavy-duty balancing cable. And the reason I'm doing that is I want to try to use my flying capacitor's active balance board, which I have on my other solar generator, which incidentally has a very similar problem. And this was a solution. Although I think the problem here is a little bit different. But I'm going to give this a try. Before I connect it, I'm going to check my wiring here. I believe the black wire would be ground, so yeah. So here's ground, that's negative. Pack negative. Then I have a green wire, which should be going to battery 1, and it is. I also have a yellow wire, which should be going to battery 2, or junction 2. And then I have a white wire which should be going to junction 3, and it is, right up there. And then I have a blue wire which should be going to the pack positive, the actual pack positive, not the fake one that comes from the BMS. Now I'm going to try plugging in my flying capacitor's balance board using the wrong cable, but hopefully it won't care, and see if it will help me. I heard it come on right away. You can hear a high-pitched sound. Now what I really hate about this setup here is I cannot watch the cells to see what they're doing. I hate that. I don't have a 4S connector to do that. So I'm going to have to use my voltmeter. Very inconvenient. But that's what I can do right now. I went to eBay and I ordered some 4S balance leads so I can do this right. But let's measure that low cell. It's I don't remember which one it was. Here's the ground and B1, 2.9. It shot way up. It went from 2 to 2.9 volts. Now it's also very possible that this cell group has a short in it. I sure hope not, but it's possible. That voltmeter, I'm going to replace it with this voltmeter so that I can see the voltage in real time without holding the probes on there. So I really don't want to dump that kind of current into the cell, but I'm out of time. And I want to get the split back together and work on other things. So this active balancer doesn't care about the condition of the cells, it just slams the current in there. There's advantages to that, there's also disadvantages. It's already up to 3 volts. This thing is getting really warm. Wow. This flying capacitor's balance board is getting really warm. I might have to put a fan on it. It's not playing around. I don't know how many amps it's putting in there. A little bit too warm for my taste, so let me try a power supply. If I use like a small bench power supply and connect it directly to that cell, that would be a better way to remedy this condition. I managed to get my small power supply connected to the cell that is the lowest. That cell was sitting at 2 volts. 2 volts is over discharged, and so probably it damaged some of the cells. Here's the setup. I have my flying capacitor's active balance board 4S hooked up temporarily from my other power bank, and that's dumping I don't know how much current into the cells that are low and pulling it out of the cells that are high. I have this USB fan cooling the balance board because it does tend to get a little warm. The thing about these boards is the current rapidly falls away. So now that I'm charging this cell and I got it up to 3 volts, the really low cell, this thing is not pulling as much current. There's not as much imbalance and it's running a lot better. Just in case, I put my little fan here to cool the MOSFETs underneath. Here I have a bench power supply charging the really low cell at 800 milliamps on top of what this board is doing. And then I have a multimeter measuring that same low cell to see what it's doing, because I need to keep an eye on it. I added another multimeter here, and I'm going to go ahead and check the cells again. There's 4 of them. Now here's a really tricky thing. I have to probe battery junction 2 and battery junction 3, and if you make a mistake you will short out a very big lithium-ion battery. 3.4 volts. 3.4 volts is a lot better than what we had before. So that's looking a little bit better. No, it's not balanced, but it's less of a disaster than it was an hour ago. One of the cells is up to 4 volts. I don't remember which one that was. Okay, B1 and B2. Let's try measuring that. 4 volts. So that was the high cell. And that one is going to be coming down now because this balancing board here is tearing it down. That's going to take a long time though because that's way out of balance. That cell was basically full. The others were basically empty. Well, I really don't like doing this, but I have a 5S. And I'm just going to cut that off. Cut one end off. And only use 4 of the wires. Sorry, 5 of the wires. And I have several of these. Might as well use them. Nice and neat. I'll just cut one wire off. So I only need that many wires. This will do the job. It doesn't really matter how it looks, and it could be a week before the correct kind of connectors come. So rather than waiting, I'll just go ahead and use this one. So now in the lower left hand corner of the screen I'm just putting some solder on this balance header here. And I'm going to try to solder these on in the right order. Hopefully I get the order right. It's quite a few wires to connect, and you got to get them right or it won't work. So I'm just soldering on the balance header. And I may come back and redo these connections later. And the trick here is to get the order correct. So the second wire goes to battery 1. And before I do this, I'm going to disconnect my active balancer, just to be safe. Just going to temporarily tack this on here. I will might do some upgrades to this later. But right now I just need to be able to measure all the cells for safety reasons. It's not safe otherwise. Really need to see what's going on. Okay, I just barely nailed that one. Now the next wire. That would come around to B3. Okay, that's going to need a little more work. I don't want to get it too hot. Alright, I'm just going to let that go. It's not pretty. This might get reworked later. And then this is going to go to the positive. And that's going to be tricky also. Let's see if I can get that on there. I'm not using the red wire. See if I can just get on right here. Yeah, it's good enough for now. Hopefully now I can measure the cells using my battery computer if I hook this up correctly. See, that's negative. Let's see if I can get this to come on. There we go. So there's the first look at the cells. Cell 2, yeah. So they're much better than they were when I found them. Could have been worse. Alright, we had a good thing happen here. The BMS appears to be doing its job. It's now putting out pack voltage. 14.8 volts. That's on the main discharge. So this battery pack was protecting itself the best it knew how. I should say the BMS was doing the best that it could, I guess, to protect this battery. And it was basically saying that, hey, one of the cells is down to 2 volts, so you're not allowed to use the pack. Strangely, though, when I charged the pack, it didn't seem to be able to balance it. I'm going to say the battery protection circuit part of this battery pack here is working correctly. The other part of it, the balancing part, I have my doubts. I don't think that's working correctly. Now, one way you can test a BMS, feeling for heat when it's not supposed to be balancing. If you feel any heat, that means it's balancing when it's not supposed to. And this one's ambiguous. It's hard to tell. Of course, I have been charging it. It could also be that this thing switched off the balance part of the circuit and it just kind of gave up and went to sleep. That's possible. And I'm looking at the cells here to see if they're changing, which would indicate balancing. And I'm really not seeing anything. I hate how this thing goes to sleep and turns the screen off. Wish I could disable it. But I love this little computer, very useful. It's hard to tell whether this thing is in balancing mode or not and trying to balance the cells. It could be. It could just need a little boost to get going. So what I'm going to do is give us a good balance charge myself using my own capabilities and then see if this BMS is able to hang on from there. I'll never deep discharge this battery pack. That's probably what happened to it. And when these battery packs are deep discharged, it could be this particular BMS doesn't handle that too well. Let's go ahead and attach the active balancer and see if that does anything. Gotta make sure I hook it up correctly. Active balancer is on, and you can see that the voltage is already changing. And you can see the delta, which is right here, 608 millivolts, is already changing. It's dropping. So these active balancers are no joke. They really tear it up. Now normally you don't balance a pack until it's nearly full. In this case, this is first aid for a battery pack. It's badly out of balance. It's obviously out of balance. You're talking over a half a volt out, and that's why I'm doing it that way. Normally I would never want to run this active balancer until the pack is nearly full and reaching the end of charge, or if there's a really bad imbalance that manifests even when the pack is at partial states of charge. So these active balancers are great for getting a battery back into balance. In this case, I'll probably just leave the active balancer on there. They work so well. I've had a good experience with them so far. So basically there's nothing to do here but watch this thing go into balance. I think what I will do is reassemble the power system, put the battery back in it, and leave all my balance connectors connected, touch up the solder joints, and go ahead and put this thing into service and see if I can keep it in balance. If necessary, I can remove the BMS and replace it with something else that doesn't balance. Ideally just a battery protection circuit, not a balancer. And I'll do the balancing using my flying capacitors active balance boards. They're not cheap, but that's because they work. I now have the battery taped back up with some tape that I had. I put multiple layers on, insulated the wires. I have my flying capacitors active balance board header right here. That's the big thick wires. I have a standard JST XH connector here so I can check the battery balance. I can also balance through here if I want. And now I can just drop this back in, and I'll have all these extra connectors if I need them. Now there's nothing to say I won't come back in here later and take all these connectors off and redo it. Right now I suspect this battery is usable, but I'm not willing to go too far until I'm really sure, and I'm not really sure yet. I hated tearing the battery up, but there was no way to get this thing to work correctly. Basically this battery was bricked and it was refusing to charge properly. It was not going into balance. I don't really believe this BMS is capable of handling such a severe imbalance, which is unfortunate. A lot of extra wires here. So I've got a lot of the wires crammed in there. I have this connection here, a JST-XH 5S, so I can monitor the battery anytime I want to. This will be left permanently connected. I have a heavy-duty balance connector here for my flying capacitors active balance. This will allow me to quickly balance the battery if I need to. For right now, I can close this unit up and start using it, and I will have access to monitor the battery anytime I want to, and that's what I need. And I need to be able to get in there and just check things anytime if I think there's a problem. And then once I figure out if the BMS is the problem, I can open it back up and replace that, or actually just remove it. Before I close it up, there's a look at some of the wiring. There's a lot of wires in here now. The inverter I'm not going to be worrying about right now, so I won't be powering that on. This unit is no fun to put together with all of those wires in there, but I've almost got it together. I can go ahead and give this a test and see if I'm going to be able to do anything with it. The batteries are still out of balance, so I'll have to leave it running for quite a long time balancing. But I'm willing to do that to see if I can get any value out of this unit, because I put quite a bit of work into it. Okay, there's the front on. The back I'm going to leave off for now, so I have access to all my diagnostics and wires. That's not really a problem. Now I need to put the screws in. I'm actually missing a screw. I don't know if that means somebody got into this unit, or I miscounted the screws, or I dropped one. I don't know. Nothing inside looked disturbed. So I'm just going to put enough screws on here to hold it together, and then I can go ahead and try to test this thing and see if I can do anything with it. And I forgot to put the handle in. There we go. Make sure I don't pinch the wires. Alright. I put a couple more screws in the top here for safety reasons. Probably one right here at the corner would be good. See if we can get some power out of this thing. Alright, the flashlight's working. Let me see if the display works. I scratched the screen up a little bit. So it's alive. Now the question is, will it charge? It's on. Let's see if it will charge. Now the question is, what are the cells doing? And I have a diagnostic cable now that I can plug into. Way out of balance, of course. I expected that. I hope the camera is able to show the display. You can see what a disaster that is. Completely out of balance. So now this allows me to charge it without being afraid of any issues that might damage the battery. I can watch these cells and I can make sure they're behaving. I seriously doubt that this BMS will be able to pull it together. Once again, just checking to see if the inverter will power on while the unit is charging. As you can see, it does not. So it's not a solar generator at all. But it is what it is. There are still uses here. I'm going to abandon the inverter for now and just use the USB and DC outputs. I still am not convinced that this unit is charging properly. Anytime I charge it through the DC input jack, it acts a bit strange. But that's not necessarily an issue that I couldn't fix by simply adding my own charging circuit and rewiring the DC input jack to connect to that circuit instead. So not the end of the world, and actually a pretty easy problem to fix. Did a bit more testing, and unfortunately when I charged the unit through this DC input, which goes all the way through and over to this circuit board, the charging circuit cuts on and off, on and off. It just keeps doing that over and over again. Well, that doesn't work for me. So what I did is I ran my bench power supply straight to the battery connections on the circuit board, and it charges just fine. But that is a pretty easy problem to solve. What I will do is just wire that input jack directly to the circuit board and bypass the charging circuit, which may or may not be malfunctioning. It's really not a deal breaker. And then I'll just use a constant current, constant voltage DC converter to charge the battery myself, and that way I can customize the charge voltage to something more reasonable, like 16.2 volts or something like that. I really don't want to fully charge the battery anyway, and that's usually how I handle my lithium batteries. Of all the things that could break, that would be one of the easiest to solve. The battery balance has been improving for about an hour now. It's now 430 millivolts differential. Still out of balance, but it's looking a lot better. So really all I have to do is let this balancing finish, give it a decent charge, probably 90%, and then do a load test on it. Just to summarize, this unit was in a brick condition and would not charge. The fault is that the battery pack was way out of balance for some reason. I regrettably opened it up and tore open the battery pack and found that to be the case, meaning that it was unbalanced. So I did a manual balance charge on it, and I attached two balance headers to the battery, kind of like medical first aid for a battery pack. And I'm now getting the battery to wake up again. It puts out power. It's still out of balance, but it's improving. The only step left beyond that would be to probably wire in my own charging circuit and basically put this thing into service. It looks like it will have some capacity in it. Who knows how much power it's got left. I'm sure that cell number 1 was damaged from its deep discharge. One of my USB camera lights is so bright and draws so much power from the USB port, it often shuts off my other portable power system when I turn it on. This power station here doesn't even care. If I plug it in, it has no problem whatsoever. That's probably because this one has USB 3.0 quick charge as well as USB-C. It's not having any problem at all running a high-powered USB light. It's very likely this power station here will be pressed into service for lighting duties mainly, including running my camera lights. And I should be able to run 2 or 3 lights now off of this unit. And it's nice to have extra power when you need it. On the output of this power unit, I'm getting a regulated 12.6, 12.5, 12.6 volts, something like that. So there's a DC-DC converter in here that's regulating the outputs. I prefer direct access to the battery myself, but that is how they built this unit. It's running a 4-cell system, which is too high in voltage. That would be way above 12 volt nominal voltage. So that's why they have a regulator in there. The problem with that is you can't really connect high power stuff to it in many cases. This unit has very tiny electronics. I don't believe you could run any high power 12 volt appliance, and I believe the outputs are rated at only a handful of amps, like 3 amps, but you could run a desk lamp. I do use an LED desk lamp that's 12 volts, so that would run no problem. This unit is not scrap after all, it's just got some problems, and after some poking around and soldering and tearing things apart, it looks like it's going to serve me well. And there's the finished product. It's able to run my USB-C soldering iron with no problem whatsoever. It's simultaneously running my most powerful camera light, no problem at all. The cell balance is a lot better. It's around 50 to 100 millivolts. You can see it detects which output is active. The cell balance is looking pretty good. It's not perfect, but it's better than it was. It will take a while. I bypassed the internal charging circuit because I don't trust it and I don't think it's very reliable. And it could have something to do with the original reason for this unit failing in the first place. So I just ran it straight out the back to the BMS charge input, and I'll use that for now to charge the unit. Suits me fine. I'll be able to control the voltage. I can't say that about the original charging circuit. It does not let you control the voltage. I'm not going to worry about the inverter right now. It shows some signs of life, but I really don't need it, and maybe it would make a nice project for later. I think I will cut the video short here as it's extremely long. If anyone is interested in knowing how to install your own charging circuit in one of these portable power systems, or a solar generator even, let me know and I'll go ahead and produce one. It's not a terribly difficult process, but it can be hard sometimes fitting the circuit inside the case, and also finding a DC converter that will work properly as a charger and does not drain the battery when it's in standby. You don't want a DC converter that's going to slowly run the battery down when it's not charging, and that can be rather tricky to avoid that problem. I hope you enjoyed this video. Thanks for watching, and I'll see you later.